morning again to everybody. It's it's my duty, but it's also a great pleasure for me to chair this session, which is devoted to the Terzaghi Oration. The Terzaghi Oration recognizes a person of distinction who has made an outstanding contribution to geotechnical engineering. It normally covers case histories and the interaction between research, teaching, and practice. The orations demonstrate that Professor Terzaghi's intellectual, practical, and observational approach to engineering and geology. This 2017 oration explores some of the difficulties involved in translating research into practice and the relevance of current research to real-life geotechnical engineering problems, particularly in a developing country. This will be the approach which our recipient, Dr. Peter Day, has chosen to deliver to us today. Peter had his Master of Civil Engineering at the University of Natal in South Africa and his Doctor of Engineering at the University of Stellenbosch in South Africa. From 1979 to present, he is a geotechnical consultant with Jones and Wagner in South Africa. From 2013 to present, he is an adjunct professor in geotechnical engineering at Stellenbosch, the University of Stellenbosch. He is a professional engineer and is the past ISSMG Vice President for Africa. Peter, we are listening to you now with great pleasure.
Thank you very much, Mr. President, for those kind words of introduction. And thank you to the International Society for affording me the honor of presenting this Terzaghi Oration. And it is indeed an honor for me and for the Africa region. And thanks to Professor Kim, the chair of the organizing committee, and Professor Yeong, the president of the Korean Geotechnical Society. From what we've seen so far of this conference, it promises to be a great event. The topic of my talk is challenges and shortcomings in geotechnical practice in the context of a developing country. I'm a consulting civil engineer by profession, consulting geotechnical engineer, and I want to lead off with the plaque in honor of Carl Terzaghi. It reads, a civil engineer. He lived without compromising. He served his chosen profession to the best of his abilities and died without having anything to regret. Few can doubt that this very simple equation was the beginning of theoretical soil mechanics. And we've come a long way since then, from the rudimentary experiments carried out by Terzaghi himself to the most sophisticated geotechnical testing equipment that can be bought today. From hand calculations of earth pressures to numerical analyses with any choice of different constitutive models. From field tests to determine the elastic modulus of a single portion of soil or rock, which could take weeks to execute, to geophysical methods of determining the small strain stiffness of material in the matter of a couple of hours to depths in excess of 20 meters. We've made enormous strides since 1925, but there is a question to be asked. What if the problems we are solving are not the right problems, or if the solutions either are not or cannot be implemented in practice? And I want to look at that a little bit more today. This is the outline of my presentation, and it's going to lead in conclusion to 7 simple statements. I'm a practicing engineer. I keep things as simple as possible, including fieldwork. So we'll start off with some very simple case histories. I cannot hope to compete with case histories like tailings dams failures, like the Nickel Highway failure, or the collapse of the London Heathrow Tunnel, or anything of that nature, and I don't intend to try. I want to present very simple case histories, all of which have a clear message. They all come from South Africa. And just to step back a bit, South Africa, situated on the southern tip of the African continent, population of 54 million, and a GDP growth in 2016 of 0.3%. So we're not only a developing country, we are a very slowly developing country. Compared to South Korea, approximately the same population, but with a far smaller landmass, giving it a 12 times higher population density than that of South Africa. About 3 times the gross domestic product per capita, and a 2.8% growth rate. The 5 case issues that I'm going to deal with are shown on this slide. And the first one, just to demonstrate the simplicity of my approach, deals with sub-economic housing in the area of Bloemfontein in the center of the country. Typically, these projects are undertaken on very limited budgets, and very often the site investigations are found wanting. Poor laboratory testing is carried out, and as a result, incorrect foundation types are used. And this is particularly surprising because in South Africa, we have been pioneering research into expansive soils since the 1980s. My next one is a slightly bigger case history or bigger structure, a 3.6 gigawatt power station, a thermal power station on expansive soils, where up to a meter of heave movements were experienced within the first 5 years after construction. And the reason for that was the site was covered with a plantation of eucalyptus trees or blue gum trees, and the soils had become deeply desiccated. And even though a very thorough investigation was undertaken, the problem was simply not recognized despite a similar occurrence having taken place 15 years earlier. Next case history is down in the Cape Peninsula near Cape Town on the back slopes of Table Mountain in a suburb called Camps Bay. And the house which we're going to be looking at is right at the upper end of the slope, so on one of the steepest gradients of about 1 in 3. And this is a case of excavation-induced instability. No geotechnical investigation was carried out for this fairly major excavation in a steeply sloping hill slope. The history of slope movement was totally ignored from the 1980s onwards, and retaining walls were designed without any consideration of overall stability. The critical failure mode in this case was simply not recognized. My next example comes from the Sandton Business District, just north of Johannesburg, and it's a case of a 32-meter deep excavation where the investigation consists of widely spaced auger holes, most of which terminated at a depth of approximately 20 meters, and rock levels were extrapolated. During construction, no rock was encountered to the full depth of the excavation in places, and a total redesign of the lateral support was required, requiring backfilling or partial backfilling around the perimeter of the excavation for the installation of longer and higher capacity anchors. The basic investigation requirements were totally ignored. The final example comes from Pretoria, the administrative capital of South Africa. It's a structural collapse on adversely dipping shales during construction. An adequate investigation was carried out, and the adverse dip of the shales was clearly recognized. However, during construction, a decision was taken to change the construction sequence, with a building higher up the slope being constructed before a building lower down. And the construction management decision ignored the critical geotechnical information contained in the report. In all these case histories, there is a common thread. The knowledge required to prevent these failures existed, but not the will or the resources to apply that knowledge. We have similar problems with geotechnical research. The problem is not one of an absence of knowledge, but our failure to transfer this knowledge into practice. So I want to take a look at what I term the knowledge development and implementation cycle. And this is my version of that particular cycle. The upper portions of the diagram, which are in the research environment and the academic environment, and the lower portions of the diagram involve implementation by practitioners such as myself, and including contractors. Let's take a look at basic research and step right back to 1936, to the first International Conference on Soil Mechanics and Foundation Engineering. And Terzaghi is circled in yellow on the left-hand side of this picture. The topics which were discussed at that conference and the following conference in 1948 in Rotterdam were fundamental topics such as soil properties, foundations and settlements, earth pressures, slope stability, and so on. And these were keenly followed and probably fully understood by all the delegates to that conference. If we compare that to what we have today with the Paris conference and this conference here in Seoul, we're dealing with topics as esoteric as earthquake engineering, offshore geotechnics, physical modeling, urban geohazards, and the like. There is a tendency towards increased specialization, requiring parallel sessions for anywhere up to 2,500 delegates at our international conferences. During 2012, 20 million first degrees were awarded. 6.4 million of these were in science and engineering, and approximately half of them were awarded in both China and India combined. 116,000 doctoral degrees in the countries which are listed on the slide, and you can clearly see the growth trend, particularly in countries like China, and South Korea and Thailand are also growing, but off a lower base. Estimated 5.9 million researchers in science and engineering alone in 2013. As far as research publications go, we passed the 50 million mark for peer-reviewed publications in 2009, and 1.5 million of these were added in 2009 alone. Elsevier, just one of the publishing houses for scientific papers, published 400,000 manuscripts in 2015. 17,850 papers were published in geotechnical engineering and engineering geology in 2015 alone. And I can show you that I read a very small fraction of those. 292 journals, just in engineering geology and geotechnical engineering. The result is a total overload, and the average practitioner simply cannot keep up. But more importantly, the average practitioner has no way of assessing the value and the reliability of findings of the research which is being produced. So it is essential that we move on to evaluation of this research and its translation or its conversion into information which is usable within the profession. Ralph Peck said, "It should be by no means assumed that the latest scientific advance is always in the right direction." As far as evaluation is concerned, I think literature reviews are very important. But the most important to me are research to practice papers, not so much state-of-the-art papers, but research to practice papers, such as the seminal paper published by Poulos, Carter, and Small at the Istanbul Conference in 2001. It enjoys pride of place on my bookshelf if it is not on my desk. And ISSMGE Technical Committee special reports are invaluable, and the technical committees are doing a marvelous job. Conversion to usable format. The first uptake is usually with computer programs that incorporate the latest advances into code. Industrial guidelines produced by various organizations. Textbooks tend to lag, and codes of practice lag even further. But these all convert knowledge into usable format. Next, the knowledge needs to be transferred to industry, and this occurs at two levels. The training of new geotechnical engineers. And I'm sorry to say that here in the 21st century, there are still so many tertiary institutions where soil mechanics and geotechnical engineering is being taught by lecturers who haven't changed their method of lecturing or their lecture note content probably for the last 25 years. It occurs far too often in our situations. We need switched on, enthusiastic and inspirational educators. they need to be experienced and professionally registered, particularly at the outcomes level of our education. And the possibility is now becoming a reality of internationally accredited web-based undergraduate sources, which will take a lot of pressure off the universities and set them free to do more research. Continuing professional education or development is the way in which we keep practicing engineers up to date. And here, seminars and workshops, speciality conferences, not broad-based conferences, but speciality conferences, including regional conferences, and open postgraduate courses are particularly important. The latter is my favorite. All my postgraduate courses are open to the profession. Implementation in practice. I want to look at the requirements and the barriers. First of all, the requirements. There needs to be an awareness of the existence of the knowledge, an understanding of that knowledge and how to apply it. There needs to be a clear recognition of the benefits which will result from its application. And we need the data. Very importantly, we need the data to be able to apply the latest advances. The main barriers to implementation, I think, are simply inertia. Take, for example, working stress design. We've always done it that way in the past. Why should we change now? Slightly more subtle, not yet the accepted norm. In other words, you're not afforded the protection of adhering to the norms of the profession should something go wrong. A lack of any perceived benefit, particularly in a competitive environment such as we find ourselves in today, or the required data or the equipment needed to implement the new findings is not available. We next move back, so we then move on to a very critical part of the cycle, which is the assessment of the performance of new knowledge in practice and feeding it back to the research community. And the assessment takes place at two stages, particularly at the design stage, where it can be applied to completed projects or case histories, new theories can, and we can apply those new theories to compare with existing methods of calculation. And at the construction stage, the application of the observational method with field monitoring and comparison with predictions, and then also back analysis of performance at the end of the project. So that's the idyllic cycle. That's how it's supposed to work. But unfortunately, the two vertical arms of the cycle seem to be severed in so many instances. We actually need a paradigm shift in which the winnowing, communication, synthesis, and implementation of knowledge enjoys the same priority as the creation of new knowledge. Then something very dear to my heart is geotechnical design codes, and I've spent many years of my life contributing to geotechnical design codes. And here I want to tell you that South Africa is a totally unique country. From the iconic Table Mountain standing guard over Table Bay to the carpets of daisies which appear in Namaqualand at about this time of year, to the view from our farmhouse on a clear day. This is our farmhouse down in the Mpumalanga Escarpment, where we go over weekends on a clear day. It's also unique in that we are the only country in the world to have held an ISSMGE board meeting which was interrupted by elephants, held in Moshlebetsi on the outskirts of the Kruger Park. And what could be more uniquely South African than a bush sunset or the inevitable braai or potjie kos, which follows after, with conversations going on deep into the night. But there's another thing which is totally unique in South Africa, our geotechnical or our design standards, our national standards. South African standards are not mandatory. They are simply a statement of good practice. They're written by volunteers with absolutely no compensation and no recognition. They're generally based on foreign codes. And something which we're trying desperately to remedy at the moment is that we have no geotechnical design code. So what are the options we're considering for a geotechnical design code? And I'm sure that there are many other countries whose representatives are sitting in this audience who are facing the same dilemma. Working stress design is one option. Simple to use, but unfortunately fundamentally flawed because the factor of safety is a poor measure of reliability. Limit states design, which is the current international norm, criticisms here is that it creates an artificial distinction between the ultimate and the serviceability limit state. And there's a perceived complexity, particularly with the Eurocodes and their multiplicity of design approaches. Partial factors are seen as being somewhat arbitrarily selected, and the subjective selection of characteristic values remains a problem. Mobilized strength design by Malcolm Bolton and his colleagues designed on limiting the strains within soil to acceptable levels rather than the stresses. Unfortunately, it only applies at this stage to undrained soils. Reliability-based design, the new kid on the block, and I'm sure that we're going to be hearing a lot about it during this conference, where we account for uncertainties directly at the source of the input variables. It can be used to complement limit states design and computes the reliability index and the probability of failure directly without having to go through a factor of safety. We have difficulties in applying it with closed-form solution, and we require statistical characterization of parameters, which can sometimes be a challenge. But nevertheless, these lower two are the ones which are attracting our attention at the moment. So we are now moving into this phase of the knowledge development cycle, the evaluation and transfer phase. And as far as evaluation is concerned, what we're concentrating on is the comparison of the various design methods, and I'll describe that a little bit later. And then the transfer to industry, which is taking place by teaching reliability methods to postgraduate students in South Africa together with limit states design, and trial implementation of reliability-based design methods in practice. Our method of evaluation follows that which was adopted for the evaluation of the Eurocodes at the Trinity College Dublin workshop organized by Trevor Orr in 2005. And we've chosen 7 simple structures based on those which were selected by Trevor Orr, and only one soil type at this stage. We then find the Eurocode compliance solution for each of these structures, and then go through a process of determining the reliability index and the probability of failure using both first-order reliability methods and Monte Carlo simulation, and then backfigure the factor of safety using working stress design methods with both the mean and the characteristic values as input. And then we've repeated the process for a range of input parameters. These are the 7 structures which we've used: 3 types of footing, an axially loaded pile, and 3 types of retaining wall. Soil type is a sand with a log normal distribution of strength and a normal distribution of density and a slight positive correlation between the two. Loading, a log normal distribution for imposed loads and a Gumbel distribution, extreme value type 1, for wind loading. And these are the results expressed in terms of the reliability index for reliability-based design and the global factor of safety for working stress design. The first thing we see is that the reliability achieved by the limit states or the Eurocode compliance solutions is remarkably similar for the form analysis and the Monte Carlo simulation, indicating that form, which is considerably simpler to apply, is adequate for most geotechnical problems. There's also a remarkable consistency in the level of reliability throughout all the examples, despite the different modes of failure, which is highly encouraging. And the reliability indices are close to the target value, which lies between 3.2 or 3.8 for most classifications of structures. As far as working stress design is concerned, you will see a wide variation in the factor of safety across the different models, indicating that the factor of safety is a poor measure of reliability. The next step in the process was to look at varying the parameters, and this particular slide shows a range of strength parameters on the horizontal axis and the reliability index on the vertical axis. And you'll see that for all the examples except the pile example, which is the one in green, across that full range of parameters, the reliability index stays sensibly within that 3.2 to 3.8 range, a very gratifying result. However, with the factor of safety, particularly at the higher end of the range, there is a significant divergence in the values of the factors of safety for the different structures, varying from 1.4 to 10. If we look at just one of those examples, example C, which is an eccentric and inclined loaded foundation, as you increase the strength of the soil, the reliability decreases for this particular example. However, the factor of safety shows an increase to values far in excess of those which we would normally adopt. And if we were to adopt a factor of safety within the normal range of 2.5 to 3, we would find that we would require a significantly smaller footing with a significantly lower level of reliability. We then compared design approaches, and here we used the approach of Vogt and Schuppner, which came from 2006, and the critique of that, which was prepared by Brian Simpson in 2007. And again, it is an inclined and eccentrically loaded foundation, this time a strip footing, but also on a sand. We repeated the calculations done by Simpson in 2007, where for various ratios of the horizontal to vertical load plotted along the horizontal axis, we determined the width of the footing. And you'll see that for the conventional design approaches in the Eurocode, the width of the footing does not vary too significantly. However, the proposed design approach, the DA2 star, which combines loads before factoring them, gives a far lower footing width, required footing width. Our contribution is we've taken this one step further, and we've performed reliability analyses on the same basis as before, and we find that the traditional design approaches, DA1 to DA3, give us target reliabilities typically within the target range, possibly getting a little bit too low at the upper end of the ratio of horizontal vertical load. Whereas DA2 star gives us levels of reliability with high eccentricities which are below the target range. So what are we looking at for South Africa? We're probably going to adopt an approach similar to that in the Eurocodes, design approach 1, combination 2, and allow for reliability-based design in addition to limit states design. So at this stage, we're satisfied that we have all the tools that we need, but challenges still remain. And I think the main challenges that we face are unforeseen ground conditions, surprises which occur during construction, poor geotechnical data, overlooking of the critical failure mechanism, human error or blind acceptance of results, particularly from sophisticated computer programs, and challenging ground conditions. And I want to look, in the time that remains to me, at these two, starting with geotechnical data. And as I said to you, my intention is to keep this as simple as possible. And what could be more simple than grading and indicator analyses, grading and Atterberg limits? These two tests form the basis of our classification of soils. And let's look at some of the results which have come out of them. And what motivated this was a case history of a substation where a geotechnical investigation was undertaken, samples submitted for laboratory testing, and the soils were found to be benign. However, shortly after construction, heave cracking was noticed on this particular structure. So we returned to the site and took more soil samples and divided them and sent them to 4 different accredited soil testing laboratories. And I want to highlight just a couple of differences. The plasticity index ranged from about 45%, which is a highly active soil, down to 14%, which is getting down to a benign level. As far as the grading was concerned, the clay content ranged from 35% down to about 8%. And there's a step in the grading curve at the boundary between the sieve analysis and the hydrometer analysis. And a number of people have been looking into the reasons why this should have occurred. I've jumped a slide ahead. Sorry, this is more data, this case from red tropical soils taken from Central Africa. And a large sample of soil was subdivided and sent to 6 different laboratories situated both in South Africa and in Europe. and the clay contents received from these laboratories varied from about 62% down to 12%, a significant variation resulting in a totally different classification of this single sample of soil. The researchers who have been looking into this, Scott and Teron, from the Central University of Technology, near that first case history which I showed you of the cracked houses, indicated that the mixing time after adding of water to the liquid limit test and the use of the 1-point versus the 3-point liquid limit test accounted for an increase in the PI of between 29 and 75%. Blink and Hoortkorn, in 2016, working on red tropical soils, identified drying temperature and the mixing time for the liquid limit test. And the liquid limit varied between 45% and 85%, with the highest values being recorded for air drying and longer mixing times. Kaur and Fanarakis in 2016 looked at the hydrometer test and identified the type and volume of dispersant as accounting for a variation in the clay content of a noritic clay from 14 to 35%. We really need to sit down in a quiet place and ask ourselves some serious questions in the light of these results. Firstly, have our test methods changed so much over the past years that the correlations developed in the past no longer apply? Is there any point in doing sophisticated analyses based on test data that we cannot trust? Has our development of new computational models outstripped our ability to reliably and economically determine the parameters required? Do we need separate standards for road building materials and for geotechnical testing? Are we letting project managers dictate the scope and extent of geotechnical investigations? And if the answer to that is yes, how are we going to equip them to do this in an informed way? These are all questions that we need to think about. My final topic is looking at some challenging soil profiles. If you take a look at these 4 soil profiles from various parts of South Africa, each one of them has 3 things in common, or they all have 3 things in common. They're not saturated, they do not fit into a triaxial cell, and they're not amenable to conventional testing and analysis. Take dolomites for an example. This is a 60-meter diameter sinkhole which opened up about 60 kilometers east of Johannesburg, caused by dewatering by irrigation farmers. Water ingress is the other major source, so it means we have sinkholes in developed areas as well, where leaks develop in water-bearing surfaces. An additional problem is the formation of compaction subsidences, or dough lines as we call them, due to dewatering, particularly dewatering for deep-level gold mines, which was undertaken extensively in the 1960s and 70s in South Africa. This is Wagner's depiction of the bedrock or the subsurface topography of a dolomite site, consisting of a very pinnacled and uneven rockhead with interconnected cavities, followed by wads, slumped chert gravels in the residuum, and a variable thickness of transported soils. And you might say that that looks pretty unreal, beyond imagination. But compare it. There the pinnacles of solid rock. There the slumped chert bands. And there are the rock floaters. So how, with this extremely variable profile, as is illustrated by this exhumed chert poor dolomite in a quarry in Littleton, south of Pretoria, how on this extremely variable profile are we able to construct major structures such as the Gautrain rapid rail link between Johannesburg and Pretoria? Well, various conventional approaches have been used, such as deep shafts sunk to depths of 70 meters with the shafts being socketed into solid dolomite, or U-sections, concrete U-sections or bridges on grade capable of spanning sinkholes up to 15 meters in diameter. But there are other structures which are simply founded on spread footings, such as this one here. And this is the result from the drilling of 4 rotary percussion boreholes at the corners of a 5-meter grid. And the depth to first strike of rock varies from 8 meters to 58 meters within a space no bigger than this open area in front of us on the podium. How did the contractor tackle this one? We've long suspected that the stiffness of the dolomite residuum is stiffer than what it appears simply from visual inspection. So the contractor chose to preload the area of 30 of the pier positions with a 250 kPa preload consisting of 2,002 cubic meter blocks, and the settlements were measured. The average stiffness of the profile was found to be 110 MPa, significantly higher than what we imagined. And more importantly, there was minimal rebound on removal of the load, making it possible to place the spread footings on that preloaded profile with a significant reduction of both total and differential settlements. And work has recently been done in the 150 G-ton centrifuge acquired by the University of Pretoria, and this shows an experiment on the right-hand side of the page looking at the stress distribution below those surcharge blocks. We can also model the propagation of sinkholes from the initial void to the upward movement of the void through the profile, holding through to surface, and then the formation of the near-vertical sided sinkhole, which we saw, sinkholes which we saw in those examples from Pretoria. My next example comes from the Western Cape, in the area around Cape Town and Saldanha Bay. And here in this Google Earth photograph, you can clearly see the effect of the southwestward drift of this part of Gondwanaland. And it is magnificent country, with the incredible rock formations of the Cederberg Mountains, the wildflowers in series in the Western Cape. And these extend all the way down to the coast, where we have more arid conditions and typically the formation of calcrete, such as you could see outcropping next to the road. And the reason for our interest in this particular area was the Saldanha steel mill, which was constructed in the 1980s. This is the site of the steel plant prior to development. You can see calcrete outcropping on surface. If you put a dozer into it and rip the material, you'll find it breaking out in these enormous slabs, which are referred to on site as grand pianos. Beneath the bands of hard pan calcrete, we have loose calcareous sands, which can be raked out of the sidewall with a geological pick with extreme ease. And you can see the very big difference in the excavated spoil in the right-hand picture. If we drill a hole into it, we have 12 meters of that calcareous material, followed by a further thickness of Cenozoic sediments, and then clayey silts from residual granite going down to granite bedrock at a depth of 60 meters. Challenging conditions because of the hard pan calcrete, the depth of the profile, and the presence of a high water table. Again, looking at development in the area, we suspected that there was a very high small strain stiffness of the material, higher than what we were able to measure either in the laboratory or even using large-scale field testing. And we looked at the plant which we were about to construct, and we realized that the foundation bearing pressures were on average fairly modest. The entire mill building only exerts an average pressure of 85 kPa. The Correx Tower, the tallest structure on site, 160 kPa under a raft foundation, and most of the remaining development is relatively light. So we adopted an extremely simple approach, using the materials which we had on site and the equipment which we had on site. We conducted a full-scale load test capable of loading the swell down to a depth of 60 meters in the form of a 50-meter diameter by 5-meter high embankment with simple measuring devices measuring the settlement at depth. Those are the results obtained, and we could backfigure the elastic modulus profile with depth. As luck would have it, this corresponded very well with Stroud's method of interpretation of SPT results. That's Stroud 1989. And you can see the good agreement, and this enabled us to be able to extrapolate to other areas of the site. So here, with simple methods and equipment on site, we were able to perform large-scale measurements of small strain stiffness in a profile 60 meters deep. And that enabled us to found at least the major structures on spread footings. The last case history which I want to deal with, or the last difficult soil condition, is open cast mining spoils. And we have a large number of coal mining pits, open cast coal mining pits in South Africa. This is Grootegele Colliery in the northwest of the country, 2.5 kilometers wide and 90 meters deep. It's already been partially backfilled with up to 50 meters of backfill. And the remainder of the backfill is going to be placed by mechanical stacking. The overburden, interburden, etc. will be crushed in the pit, conveyed back to the back end of the pit, and then stacked with stacker reclaimers. And to facilitate that, we had to construct a platform of an additional 40 meters of backfill on top of the original 50 meters. This shows the platform in the initial stages of construction. The initial 50 meters of backfill shown in the bottom right-hand corner, and the additional 40 meters of backfill on top of it. So how did we set about predicting the settlements of this material, particularly when we're putting structures on it, which look like this, fairly heavy and with mechanical equipment which needs to stay in alignment? These are the stacker reclaimers, incidentally, or the stackers, rather. How did we set about predicting the settlement? Well, there are three phases or three major components of settlement to backfill. The first is intermediate and consolidation settlement. Because the material is coarse-grained and unsaturated, it consolidates very quickly, and we get typical drained elastic moduli of between 4 and 15 MPa. Then there's collapse settlement due to wetting up of the material, saturation. And this occurs either due to a rise in the water table or due to surface water ingress. And the best predictions which we can come up with are between 2 and 14% of the wetted thickness of the material. Just an example of what happens if you allow water ingress into uncompacted spoils next to a railway line. And then the joker, the wild card in the pack, is creep settlement, which carries on for a significant period of time. Our typical values of alpha range from 0.15 to 0.8. And we do not know at this stage whether collapse settlement, which results in a rearrangement of particles, will reset the time clock. All of this remains to be discovered. So prediction of settlement. To predict or to measure the elastic modulus, what we did was, prior to constructing the additional 40 meters of material, we buried monitoring tubes underneath that fill, extending 150 meters into where the additional fill would be placed. We then placed the 40 meters of material on top of these monitoring tubes and recorded the settlement using a hydroprofiler. And up to 2.5 meters of settlement was recorded, giving an elastic modulus of between 10.6 and 13.6 MPa for the three tests that we conducted. Creep was predicted using a creep alpha factor of 0.7, and the magnitude of creep over 20 years was predicted as 1.1 meters. However, over the first 5 years, we've already had more than 1 meter of settlement, and the plant needs to be re-leveled to keep it running smoothly. And this, we believe, has been influenced by filling in surrounding areas. But the thing which has really caught us by surprise is the significant horizontal movements which have occurred within this fill material. I'll move on now to my conclusions. And as I said, this is going to take the form of 7 simple statements. The first statement is that most geotechnical problems are not caused by a lack of knowledge, but failure to apply the available knowledge and failure to recognize critical design situations. Or in the words of Ralph Peck, who's far more succinct than I am, our practice falls short of our knowledge. Statement 2, our ability to create knowledge far outstrips our ability to translate this newfound knowledge into practice. This knowledge development cycle of mine reminds me of a Ferris wheel. And so let's give this Ferris wheel a bit of a turn through 90 degrees. And this has the effect of placing research and practice on a par instead of one below the other. Leading me to my third statement. The creation of knowledge and its implementation in practice are equally important to our profession. But rotating this diagram also gives a prime spot to the conversion, the assessment and conversion of knowledge and its transfer to industry, leading to statement 4. The consolidation and application of existing research findings should enjoy the same recognition in academic circles as new research efforts. And this will have a significant effect on the way in which we choose the topics for research. Ralph Peck again. Translating the findings of our research into simple concepts and procedures for the guidance of practicing engineers is a duty and a worthy activity of our profession. Statement 5. Practitioners and academics should see themselves in the same camp. The best research which is turned out by our universities is industry-sponsored research where industry and academia work together. Terzaghi's words were, "Theory is the language by which the lessons of experience can be clearly expressed." Statement 6. Meaningful quantitative analysis of geotechnical problems cannot take place without adequate site investigation and reliable data. In Terzaghi's words, "I can state from personal experience that the savings associated with inadequate investigations are entirely out of proportion to the financial risks." And then my final statement. There are geotechnical problems that are not amenable to theoretical analysis using classical soil mechanics methods. And this calls for ingenuity in our approach. Terzaghi said, "Soils are made by nature, not by man, and the products of nature are always complex. As soon as we pass from concrete and steel to earth, the omnipotence of theory ceases to exist." And then the final quote from Terzaghi. "To acquire competence in the field of earthworks engineering, one must live with the soil. One must love it and observe its performance, not only in the laboratory, but also in the field." Thank you.